a group. You guys have a group of 3 or 4. What I would like you guys to do as a group is take a look at this. On a frigidly cold morning of my birthday, I have a birthday balloon. All right? I take my birthday balloon outside from the dollar store because that's where you have to buy balloons now. As a group, I would like you to discuss what's going to happen to my balloon and why. Talk now. Talk as a group. Talk as a group. Helium balloon. Talk as a group. We do not need Chromebooks right now. You can close your Chromebook.
Well, I mean, like, I guess it kind of, depending on the balloon, like, if it's like a standardized latex balloon, then it probably wouldn't pop because the tear would allow the entire thing to start.
It's like this balloon.
But if it's like that balloon, actually, yeah, maybe it would just like.
It's like this balloon.
Just like get a tear in the region, then it wouldn't pop because those balloons don't really pop. They just kind of like tear open. Cool off and just go.
What happens and why? The why is my most important part of this.
Do we need to write?
No, just talk. I got paper towels. Actually, I might have some.
Remember last year in this
Okay. Nick had his hand up. Nick, what did your group... All right, shh. Nick, what did your group discuss?
We'll defer, Cody, and
You're passing? What did you guys say?
So pretty much this, like, so the balloon is hotter because it was in the room temperature, but when it goes outside, like the cold, it like causes it to pop. Like not pop necessarily, more like just create a tear, because if it's that kind of balloon, those balloons don't really pop.
Okay. So they're saying the cold causes it to pop. Anybody else discuss something different than that? What'd you guys say, Alan?
We said it would shrink.
It would shrink. Why?
Because, I don't know, I just know it would.
Because we don't know. Oh, you're coming back now? Tara, you already deferred on this one. Bodie.
Maybe because like it came out of the hot temperature of the room, and the particles came faster than when it got outside. The particles started slowing down, which caused it to not like flow.
Oh, we got particles slowing down. Okay, what'd you guys say, Nigel?
It'll expand because the air outside is colder, and so the particles are moving slower, so they take up less space.
Okay, we have another expand. So we got 2 groups saying it's going to get bigger. What'd you guys say, Sarah Beth?
We said that. Wait, it'll like the particles will slow down and it'll like deflate.
Deflate.
I never really explained why it is. So like, you know, like pans, like whenever you like use a pan to heat stuff up, and
Yes.
like your dad tells you, oh no, don't put cold water on it yet, and like because like whenever you put like the cold on the hot, no, not the steam, it'll literally just cause it to snap.
Okay.
Because that's how I don't remember the exact reason why, but it would work the same with the balloon.
Has anybody ever done this? No. No one's ever taken a balloon outside in the winter?
No, because I don't have balloons.
Okay. First of all, what cannot change about this balloon?
The mass. It's mass. The mass.
The mass can change if you lose air.
This balloon is sealed.
So it's the air.
Can the temperature of the balloon change? Can the pressure of the balloon change? Well, first of all, we have to define pressure. What's pressure?
It's not a force put against the side.
It's the amount of force against the side of the balloon by the what? Let's talk about the kinetic molecular theory. First thing, everything is made of particles. Second thing, particles are always hotter the colder the slower. 4, more massive particles move slower, less massive particles move faster. So, I've got temperature, volume, pressure. Can my pressure change? Is this balloon sealed? Are the number of particles going to change? No. Can the temperature change? Could the volume change?
Yes.
It could.
Yes, sir.
It could. So, I take my balloon outside. What happens to the speed of my particles? They slow down. So my particles are like this inside, right? So like here they are, each other side of the balloon. I take it outside. What do I have less of? Particles are doing what? They're slowing down. Particles are slowing down.
Less pressure.
And I have less what with the side of the balloon? Less collisions, right? So therefore my volume is going to go what? Down, right? So my balloon is going to shrink. My balloon is going to shrink. That's what you were essentially thinking, right? Yes, that's what you were thinking. So today we are talking about gas laws. We're talking about gas laws. There's 3 gas laws you guys are going to be learning today. So this is the first thing you guys have to write down. So this first one is called, we just talked about Charles' Law. Charles' Law. Each one of these are named after a famous dead guy. Yes. You're gonna find out. It's Gay-Lussac, actually. Charles' Law says, now each one of these start out with something that stays constant. What stayed constant in this first example? Pressure. So this first one was when pressure stays constant, comma. When pressure stays constant, comma. If temperature goes down, what's going to happen to the volume?
Down goes down.
The volume will also go down. Would this be the opposite if it was both going up?
Yes. Yeah.
Yes. What type of relationship would you call this?
Oh.
Negative.
Negative.
No, hey,
Nope. This is a blank relationship. Not synergize, not symbiotic, not equal. D.
Decreasing. And the 1.C. You were.
If I was going to graph this,
I know what it is. I know what it is. I can't think.
volume, temperature, it would look like that.
No, I literally know.
No, it's stuck.
It is linear, but I'm looking for the D word that goes with that. It's a D word.
Density?
Domain. Don't. Whoa. Let's play hangman. Let's play hangman. Direct.
Direct.
Yeah.
Yes. This is a direct relationship. As volume goes up, temperature goes up. So we can even write as V goes up, T goes up. The way I remember this law is that Charles watches. What does Charles watch?
Fast money.
He watches TV.
Yeah.
Charles watches TV. Charles watches TV.
Yeah.
There's an equation for this. There's an equation for this. And the equation is volume 1 over temperature 1 equals volume 2 over temperature 2. Do you guys know the cross multiplication property?
Yeah.
It's going to be really important for this math. What you do is you multiply across, right? And you divide by whatever's left, right? Because whenever you're doing a problem like this, you're always going to have 3 out of the 4. You're going to have 3 out of the 4. So I multiply across. If I have V1, then I would divide by that to solve for T2. Cross multiplication property. You multiply across, but there's always going to be something across. Divide by the other leftover thing. Charles watches TV. Charles' law. V1 over T1 equals V2 over T2. You guys got it?
Yep.
Are you ready to go back to the birthday balloon?
Yeah. Wait, is that all for Charles Law?
Yes, it's all for Charles' law. Back to my birthday party. Back to my birthday party. Here we go. Later that day, I decide to climb Mount Kilimanjaro with my balloon. Now we're going to have to pretend something here. Let's pretend that the temperature stays the same. Okay? Now what happens to my balloon and why? Talk as a group. Talk as a group. Talk as a group.
Well, like air pressure.
Talk as a team. Talk as a team.
Yeah.
Are you guys talking? I hear no talking.
Because we don't know.
We'll talk. Throw some ideas out to each
All I
other.
can think about is like air pressure, like that'll change as you go higher, but I don't really know what to do with that. Yeah, the
No, we're not. Wait, it goes up. When you go up higher, pressure goes higher. Wait, what are we?
Nick, are you guys deferring this time?
higher.
Do you want to play? I know. You're deferring again? Oh, Ava wants it.
We want it after the half. Yeah, we're gonna. Yeah, one after.
All right, Ava, you want to try? What'd your group say?
Well, because if you go up higher,
I'm going up higher.
the pressure isn't as much, I guess.
Pressure isn't as much where?
Decreases, so then the particles inside the balloon want to escape, and then it will pop.
Oh, so they're saying the balloon pops.
They punch it.
Okay, Joel?
Same idea. I don't think it'll pop, though. I think the volume will just increase.
Volume will increase. Who else? Nick, second half. Oh, you just agree.
Yeah.
Who else? Something different. Front 3 rows. Luke? No one thinks that this thing gets smaller.
Nope.
We're gonna walk the runner.
No.
We think it gets smaller.
You guys are all just, you guys are all taking a knee? We're going with the football analogy?
I said let the runner walk. I also let the runner walk.
They punted.
As I walk up the mountain, I'm getting higher to the what? Atmosphere. Also the sky, right? Which means there's less pushing down on me. Less what? Less atmosphere, less pressure. Which means there's what? Less pushing on the outsides of the balloon. Less pressure. Less particles bouncing to the outside of the balloon. Right? Therefore, the particles on the inside of the balloon can do what? Push out. So if my pressure on the outside is less, the volume is going to increase. And it could result in popping. It could result in popping. Could result in popping. Could result in popping. This gas law is called Boyle's Law. This is Boyle's Law. Good old Boyle, another dead guy number 2. He said, if temperature is held constant, so once again, we're holding something constant. If temperature is held constant, let's talk about what just happened. If pressure decreases, comma, then volume will do what? Increases. Volume increases. If pressure decreases, volume increases. What type of relationship would you call this?
Indirect.
Not indirect. Another IN word.
Indirect.
That's what they said.
Indeterminable.
Not indeterminable.
Let's play Hangman for it.
All right, Hangman it.
Can we play Hangman for it?
This is an relationship.
Internal.
Inversion.
How would the graph look? The graph would look like this. Pressure, volume. As the volume goes up, the pressure goes down.
It's not an exponential.
Not exponential.
Well, what's the opposite of exponential?
Huh? Not inconsistent.
Inverses.
Inverse. This is an inverse relationship. Inverse relationship.
We're 2 for 2 right now.
So, I like to say that Boyle, the way I remember this, what does Boyle do, Ellen?
What?
What does Boyle do? Ava, what does Boyle do?
Boil?
What does Boyle do? Charles watched TV, so what's Boyle going to do? Ellen?
Water?
Ava?
Spaghetti?
Yes, thank you. Boyle plays volleyball.
Oh, did you ask that because they play for it?
Yes. That's why Candle got it, because his sister plays volleyball.
I do too.
Oh, you do too? We should start a guys team. I'd coach it.
I dabble dabble.
Huh?
Closest team would be Mountain.
Oh, they'd crush us the first couple of years. We wouldn't be good enough.
Mount Vernon's nice.
Mount Vernon's like the home of volleyball. Boyle plays volleyball. Boyle plays volleyball. Equation is this. Pressure 1 times volume 1 equals pressure 2 times volume 2. Pressure 1 times volume 1 equals pressure 2 times volume 2. P1V1 equals P2V2. That is Boyle's law. So, inverse relationship, as pressure goes up, volume goes down. When you say indirect, that doesn't really mean the same thing as inverse.
I agree.
Doesn't really mean the same thing as inverse. You guys got everything I put up here down? Are you ready to go back to my birthday party?
Yep. Oh, cool. Wait, but I thought your balloon popped.
Well, we're gonna have to do something else then. My balloon has, you're right, my balloon has popped.
I know, it smells like burning.
They might be making pizza.
It does smell like
Hey,
burning.
we're not baking. We're not cooking that today, though.
That's smart.
Oh.
That's smart. Okay, thank you.
Oh, I hope someone brings me a piece of pizza.
It does kind of smell like burning.
All right, moving on. Later that day, my wife thinks my hair is a mess, which, you know, my hair's so long. My hair's so long. Doesn't really make sense. She decides to use hairspray in my hair to fix it up. How does the can feel when she sprays it, and why? Talk about it, this as a team. Also, what would happen if she tossed it into a fire pit? Talk as a team. Talk as a team. So we have two scenarios.
You're not uncontracting the air when you're contracting the air. It's like you release the muscle inside your blood, which allows like the air
All right. Here we go. Are you receiving? All right, you're receiving. They're starting out with, how does the can feel when you spray it?
It releases pressure.
How does the can feel?
Me.
Feels lighter.
Brielle,
The can feels cold.
the can feels cold. Who's ever sprayed a can of something? All right? When you spray an aerosol can, it feels cold. Do you have a reason why, Brielle? Wait, shh. Hold on. One person at a time. Brielle.
Because of the particles, like they're moving around, like when you're spraying it, like the pressure is going out of the can.
Shh, hold on. We got pressure going out of the can.
The particles move faster.
Particles move faster.
Yeah, because
If the particles move faster, it'd be hotter.
okay, then they're cold.
Why?
They move slower.
I agree the can gets cold. Another group. Why? Another group Y. Joel. Shh.
She said the contest. I mean,
Shh. Joel.
The pressure inside the can decreases.
Okay, but why is it getting cold then?
So why is it getting cold?
Yeah.
yeah, that's the question.
I agree the pressure is getting lower.
Because you know, like.
Wait, guys.
The gas itself was technically hotter than what it's supposed to be, because then it will get, as it gets colder, it will want to turn into like a different phase as it comes out, because now it's going into the atmosphere, which allows different temperatures to go in.
I like that guess, but no. So, in the can.
You're doing much better, big boy.
In the can. Think about this. Here's my can before I spray it. Here's my can before I spray it.
Yeah.
Particles are really what?
Close to that.
Compact, close together. How are they moving? Really fast. Why? They're hitting off of each other, right? Then I spray some out.
Now there's more room.
I got more room. Do my particles bounce off of each other as much? Are they hitting the sides of the can as much? How are they moving? Slower. That's why the can feels colder. All right? What about scenario 2? I'm going to go to,
Ava, go to Ava.
I think you've already answered one. I'm going to go to you guys.
Alright.
What happens to the can if I toss it into the fire?
The particles heat up so much you start moving like really fast.
Particles heat up, moving fast.
And like expands like the metal or plastic so it like explodes.
That's not all the way right. Nick.
It brings the boom.
Partially right. Ava. All right. Shh.
The particles move.
When you put it in a fire.
Oh wait, no, this is not great.
This group. Sarah Beth.
What?
What's going to happen to this can when I toss it in the fire? Why? Why is it going to explode?
Because it heats it up and then the particles move faster.
Heats it up. Particles move faster. But, Brielle.
Well, I was gonna say that the particles, like, since they're going so fast, they'll bounce off.
Yes, and
Once it's
why? Why is the pressure building?
Because it expands?
No.
Faster against the balloon.
What can't change? You're right. The can's volume is constant. You can't change the volume of the can. So, faster, faster, more hitting, more hitting. Can the can get bigger? Boom. Bring the boom. Brings the boom. All right. Anybody have a guess of what law this is? Gay-Lussac. Gay-Lussac. On this one, what was held constant? Volume. When volume is held constant. When volume is held constant, comma. If temperature increases, then what else is going to increase? Pressure increases. Pressure increases. What type of relationship is this? This is a direct relationship. This is a direct relationship. So as T goes up, P goes up. As T goes up, P goes up. How would this look on a graph? Pressure, temperature, straight line. Direct relationship. Everybody have a guess of what Gay-Lussac does? That would be a good way to remember it. He could play tennis. That's a good way to remember it.
He gets no playing time.
He gets no playing time. That'd be a good way to remember it. Whatever you want to do is fine. My Gay-Lussac drives a PT Cruiser. You guys put however you want to remember it. They can play tennis. They can get no playing time. They can use TP in the bathroom. All right? However you remember it. Speaking of that, guys, we are running dangerously low on toilet paper in my house. My father-in-law is going on a Costco run Wednesday. Guys, Costco toilet paper is legit not bad.
Where is the nearest Costco?
Canton. Canton. All right. Equation. P1 over T1 equals P2 over T2. P1 over T1 equals P2 over T2. So you'll notice direct relationships are over each other. Inverse are beside. Look at your yellow sheet. Get your yellow sheet out now. Get your yellow sheet out. Check out that these are already actually on your yellow sheet. Do you have these equations on your yellow sheet?
That's romantic.
We do.
You do?
Right here.
Yes.
You do?
And we have their laws.
You've got them. And you have all the variations of them on your sheet.
We have Gabe Boosnax.
Wait, why are there different variations of the
Because you might have to solve for different things. All right. You guys got this? Last thing I want to do is I want to come up with a quick unit list. Quick unit list. So, on your notes, let's come up with a unit list somewhere. Temperature. Temperature. What units can temperature be in?
Celsius.
Degrees Celsius. What else? Yeah, we're making a unit list. Degrees Fahrenheit. There's one more. Kelvin.
That doesn't have to
Kelvin. Now, do you have on your equation sheet this? Kelvin equals degrees Celsius plus 273. You're going to need to put that on your notes then. And I would add that to your equation sheet. To convert from Kelvin to Celsius, you take your degrees Celsius and you add 273 to it. What? Okay. All right, so that's temperature. Volume. What are my units for volume?
Centimeters cubed.
Centimeters cubed. Milliliters. What else?
Liters.
Liters. That's probably the main ones.
Grams per cubic centimeter.
That's density. Now, pressure. Anybody know any units of pressure? PSI. We're not going to see a lot of that because that's English. Because that's inches. Pounds per square inch.
Good job.
That's one. Another one is ATM. Anyone know what ATM is?
That's where you get money, right?
Atmospheres. How many atmospheres are pushing down on us? Another one you could see, you're right, there's one atmosphere. Another one you could see is torr, which is short for a torellini, which is this torellini. We just call it a torr. It's also the same as an atmosphere. And the other one you may see is millimeters of mercury. Millimeters of mercury. Because the first barometer was made with mercury. How many millimeters of mercury?
Why is gold AU?
Nick, why is so dumb, bro? Why is mercury
Take a look at number 10 on tonight's homework. Take a look. Oh, last one. Really quick. Really quick. Finally, I decided to deep sea dive to the Mariana Trench. What would happen to my balloon as I got to the bottom of the ocean?
It would contract into itself.
It would shrink. Because what's happening as I go down in the water? Higher pressure. What happened to those guys in the submarine last summer? They got crushed. They got crushed. They got crushed. All right. Take a look at tonight's homework. Number 10.
That's homework.
This is homework. 10. A steel can has a pressure of 1.43 ATM. So that is P1 at 298 Kelvin. So that's going to be my
Where did you get that?
T1. To what temperature must it be heated in order for the pressure to be P2? Whose law am I going to be using for this equation? Gay-Lussac. Yeah, because I have pressure and temperature.
Because volume is constant.
Right. So there's two ways I can write this. Here's how I do this. I usually just write out the original equation. P1 over T1 equals P2 over T2. Now, on your equation, right, your equation sheet, we know we're solving for what? I'm solving for T2. Agreed? Yes? Your equation sheet has that solved. If you want to write that out, if you want to say T2 equals what? What does your equation sheet tell you T2 is equal to?
Whose law? Whose law?
V2 times T1 over V1.
What?
T1 over
It's what? P2 times T1 over P1. You can write it either one of these ways. Either one of these ways. I usually just leave it like this. All right? Here's why. Because I know the cross multiplication property.
I don't. I'm so low.
I'm going to show you. 1.43 ATM over 298 Kelvin is equal to 5.65 ATM over T2. The cross multiplication property works like this. You multiply what's across. So I'm going to multiply 5.65 times 298. I'm going to hit equals and then divide by what's left. What's left? Do it. Do it. Do it. How many sig digs is my answer going to have? 3. So 5.65 times 298 divided by 1.43.
1,177.4.
But I need 3 sig digs.
1,170.
1,180 Kelvin. Now, does that make sense? Well, let's check it. What happened to my pressure? My pressure went up. Therefore, my temperature should go up. That makes sense. This sheet is your homework tonight. You can probably finish the front in the last 8 minutes we have left. Work as a team if you want to. Both sides is homework tonight.
What do we have to do? Like the gas wall practice?
Yes, the whole thing.
The back side?
The whole thing.
Oh my goodness. That's
This won't take that long. I believe in you.
Yeah.